Okay, so as I was saying, the vapor pressure is dependent on the temperature. And in this case here, this is a setup to demonstrate that. So as I was saying, we have the manometer here, which is used to measure the pressure of the vapor pressure. We have what we call a separator flask, which contains the water in it. So basically what you're going to do is open up the stopcock here, and the water will flow into the flask. And then we have this connection here, this hose connected to a vacuum. And the purpose of that is basically to pull out any air that is present inside the flask. So any pressure exerted by any gas inside here would be due to the vapor pressure of the water that will be in the flask. All right. So as stated here, the system is evacuated because of the connection to the vacuum pump. And basically, as a result of that, there's nothing here, there's nothing here. So the pressure exerted on this side of the mercury here would be the same as the pressure here. So that's what happens before you add any water. All right. Then when you add the water, what happens is that the water will produce vapor in a closed system. That vapor will exert pressure here and push up the mercury level up in the other arm. And basically the difference between these two mercury levels would represent the pressure exerted by the vapor in the water. Now, please note that the temperature here is 20 degrees Celsius, right? So that's basically the pressure that is exerted by the water at that temperature, 17.5 torr, all right? If you were to increase the temperature from 20 to 30, then there'll be a corresponding increase in the vapor pressure, in this case here to 31.8 torr. And that continues. As you increase the temperature, the vapor pressure increases, all right? And that makes sense if you think about it. Basically, as you increase the temperature, you're imparting more energy to the particles of water, and you're going to have more particles escaping from the liquid state to the gaseous state, and therefore, the more vapor molecules you have, the greater would be the vapor pressure exerted as a result, all right? And actually, there are tables. Let me just skip through this here. There are tables that have been put together, which gives you values for the vapor pressure of water for different temperatures, right? And this is one such table. There are some that are even more detailed because, as you'll notice in this particular table, the temperature increases by 10, but you have some others where they actually give you the values as you increase the temperature by, let's say, 1 degree Celsius, right? So these are the vapor pressures of water at these temperatures. And you'll notice that we have two other substances whose vapor pressures are given as well, and their values are given for the corresponding temperature values shown, all right? So different substances will have different vapor pressures at different temperatures. So what you'll notice when you compare these three substances, doesn't matter what the temperature is, what you'll find is that the vapor pressure increases, or I should say decreases, according to what you see here. Of the three substances, ethyl ether, ethyl alcohol, and water, ethyl ether has the highest vapor pressure, followed by ethyl alcohol, and then followed by water. And there are reasons for that, which we may get into later on, based on the structure, the molecular structure of these substances, all right? And that's because this trend that you see here parallels basically the rate of evaporation, right? So basically what you see is that the greater the rate of evaporation of a substance, the greater would be the vapor pressure exerted by that substance, all right? And that is seen, for example, at 30 degrees, where we have these numbers right here for each of these substances, all right? Okay, so this brings us now to a term known as volatiles or volatility. When we say that something is volatile, we basically are saying that a substance can be easily vaporized or have a very high vapor pressure, right? So ethyl ether is considered to be very volatile because of its relatively high vapor pressure. Water, not as volatile, so we can say it's moderately volatile. And then to the other extreme, if you take mercury, for example, which is a liquid, its vapor pressure is very low, right? So for most intents and purposes, we consider the vapor pressure of mercury to be 0, right? But it actually has a non-zero value of 0.0012. So therefore, because it's so low, we consider mercury to be essentially a non-volatile liquid. Surface tension, which is a property that is exhibited by a lot of liquids, water especially, it is the resistance of a liquid to an increase in its surface area, right? And the units for that is joules per moles per meter squared. Let me go back here. So the units of surface, oh, I can't. Sorry. Let me pull out my writing tool here. Yeah, the units of surface tension, not very important for you guys at this level, but it's basically the amount of energy that is needed to spread a substance, all right? A liquid. Okay, let me get back out of this. In fact, let me clear this. Okay, so that's a property that is usually exhibited by liquids, and some liquids have a greater surface tension than others. Water especially has a relatively high surface tension, and this is as a result of molecules at the surface of a liquid being pulled inward by molecules that lie below the surface layer. And I think there may be a diagram that oh shoot, I don't. Okay, there, I thought I had a diagram here which basically illustrated. Let me see if I can recreate that diagram. Okay, for some reason. All right. Here when this happens. Okay, so if you imagine, let's say you have molecules at a surface like this. So let's say this line represents a surface where you have molecules, and let's say you focus on one molecule. Well, basically, this molecule will have some attractive force existing between it and another molecule like this, attractive force here. And then you also have molecules below the surface like this. So therefore, basically the net result of that is that they tend to pull the molecules together. And therefore, that's basically what surface tension is, all right? That basically requires, in order for you to separate them, that basically requires energy, and therefore that's why the surface tension is measured in joules per meter squared. Okay, so that's basically what surface tension is all about. So as stated down here, substances with large attractions between molecules have high surface tensions. Okay, so another manifestation of the type of forces that exist between particles is what is known as capillary action, which is basically the spontaneous rising of a liquid in a narrow tube. And this is as a result of two competing forces. You have what are known as adhesive forces and cohesive forces. The cohesive forces are the forces that exist between the particles in the liquid, while the adhesive forces would be the attraction between the particles of the liquid and the walls of the tube, which is usually made of glass. And what you'll find is that if the adhesive forces between the liquid and the walls of the container is greater than the cohesive forces, then what will happen is that the liquid will climb the walls of the container, right? And basically, you're going to end up with what is known as a meniscus, which looks like a U-shaped part of the surface, which curves down, right? So basically, this is as a result of the stronger attractive forces between the particle molecules, the liquid molecules, and the walls of the cube, compared to the cohesive forces that exist between the molecules, all right? So as stated here, the adhesive forces is greater than the cohesive forces between the water molecules, all right? Boiling point. Let me see if I can go through this rather quickly. So the actual definition of the boiling point of a liquid is the temperature at which the vapor pressure of the liquid is equal to the external pressure above the liquid. That is the definition of boiling point. So it's not simply the temperature at which a liquid boils, all right? It's the temperature at which the vapor pressure of the liquid is equal to the external pressure. And then we have what is known as a normal boiling point, which is the temperature at which a liquid boils under 1 atmosphere pressure conditions, right? So if the external pressure is 1 atmosphere, then that boiling point would be called the normal boiling point, all right? So typically, when substances when their boiling points are quoted, they're quoted under normal conditions of 1 atmosphere. So we can determine the boiling point of a liquid based on the external pressure by using this information that we saw earlier, right? Remember, what this shows you is the vapor pressure of a liquid, different liquids, at various temperatures. So if you look at the vapor pressure where it's equal to 1 atmosphere, you'll see that the boiling point of water is 100 degrees Celsius, right? So basically, under the normal 1 atmosphere pressure, that's a boiling point, all right? But of course, the boiling point varies with pressure. So basically, one can predict, determine the boiling point of different liquids. As you can see here, different liquids have different boiling points, and we can get these values straight from a plot of boiling point, or I should say vapor pressure versus temperature, which I think is the next graph, right? So if you look at this graph here, this is a plot of what we saw in the tables before. We have the vapor pressure on the y-axis and the temperature on the x-axis. So if you want to find a normal boiling point of, let's say, ethyl ether, it's very simple. You just look up the vapor pressure, you mark off where the vapor pressure is equal to 1 atmosphere, which is 760, and you draw a horizontal line to see where it cuts the curve for the ethyl ether, and then you drop the vertical down here, and you can see that the vapor pressure, or I should say the boiling point, is 34.6 degrees Celsius, right? And you pretty much can do the same thing for the other substances. In the case of ethyl alcohol, it's 78.4, and of course, in the case of water, it's 100 degrees Celsius. So basically, if you have a plot like this, you can easily determine what the boiling point is under various conditions of pressure, all right? Which is the point of the next graph. So let's say, for example, you want to find out what the boiling point of ethyl alcohol is at 500 torr. Well, 500 is here. You draw a vertical line where it cuts the curve for ethyl alcohol, and then you draw the vertical line down where it cuts the x-axis. That would be the boiling point of ethyl alcohol at 500 torr pressure, all right? And then you can do the same thing for ethyl alcohol at 700 torr. You draw a line like this, and then you drop the vertical down, and then where it cuts the x-axis, that would be the boiling point of ethyl alcohol under the pressure of 700 torr, all right? Okay, let me talk about freezing point, and which is the same thing as the melting point. So basically, freezing is where you have the solid being formed from a liquid, and melting is the opposite, right? They both occur at the same temperature. And that temperature is known as a melting point, where you have an equilibrium between those two states, right? So in other words, you have this back and forth taking place between the solid and the liquid, right? Going in this direction, that's melting. In this direction is freezing. The temperature where you have that equilibrium, that would be the melting point of the substance. So that is basically what is demonstrated in this diagram here. At the equilibrium position, as soon as a solid form of water is melted, another molecule goes into the solid state, and that just continues at that temperature if the pressure is 1 atmosphere, all right? So now we're going to get into change of state. And basically, we can represent that by using what is known as a heating curve. And basically, the heating curve is a plot of temperature on the x-axis versus heat added on the y-axis. And basically, for pretty much all substances, this is the shape that it's going to take on. Now, the numbers might be different in terms of where the plateau occurs or where you have a slope. But basically, that's what you see there is essentially the shape that would that this particular plot would take on. So what I'm going to do is just basically talk about what happens at each stage, starting from below the freezing point. So we're assuming that this is representing water, right? So of course, below the freezing point, you're going to have ice. So you're going to start heating it. You're going to start heating it. And what happens? The temperature will rise until you get to the freezing point. When it gets to the freezing point, what will happen is that the freezing point, the temperature will remain at the freezing point while you have the conversion of the solid to the liquid from ice to water, right? So basically this will remain flat until all the ice has melted. When that has happened, you have water here. If you continue to heat it, then you're going to have this slope right here until you get to this point right here, where you're going to have now the boiling point of water is achieved. And of course, what's going to happen is that the liquid, H2O, will be converted to the gaseous state. So basically what will happen is that as long as you have liquid water present, the line will remain flat. The temperature will not change from 100 degrees until all the water has evaporated, and therefore you only have gas or water vapor. And if you continue to increase the temperature, then basically the temperature would increase as well as you add the heat, all right? So that's basically what happens in this particular situation, where you start from below the freezing point to above the boiling point, how the temperature varies with the heat added. So if you're given a chart or a graph like this, you should be able to tell, for example, where the boiling point is, where the melting point is, and so on and so forth, all right? Couple of things I want to talk about before I get you started on the next assignment. Heat of fusion. This is the energy required to convert 1 mole of a gram of a substance at its melting point into a liquid, all right? And different substances have different values of heat of fusion. And there's a table that we looked at which actually have values of the heat of fusion for different substances. Let me see if I can find it here. I didn't make, okay, so here's the table, right? Our main focus would be on water, right? So the value for the heat of fusion of water is 335. In fact, let me, before I forget this, let me write this value somewhere here so that, okay, so heat of fusion of water is equal to 335 joules per gram, or which is equal to 80 calories per gram. All right, and while I'm at it, let me just write down here heat of vaporization, which I'm going to talk about shortly, which is equal to 2259 joules per gram, which is equal to 540 calories per gram. All right, so now that I've written that down, let me go back to okay, let me see here. Okay, so as I was saying, the heat of fusion is the energy required to change 1 gram of a solid at its melting point into a liquid, all right? And basically, we can use that, oh gosh, okay. I thought I'd solve. Okay, so we can use that to solve problems such as this question right here, right? The question says, how many joules of energy are needed to change 10 grams of ice at 0.00 degrees Celsius to water at 20.0 degrees Celsius? Okay, so in order for us to do that, we have to recognize a couple of things. We have to recognize that there are certain energy changes that will take place at different stages, right? You're going to start off with H2O solid at 0.00 degrees Celsius, right? You're going to heat it to form H2O liquid at 0.00 degrees Celsius, right? So this is melting, all right? And then you're going to change H2O liquid at 0.00 degrees Celsius to H2O liquid at 20.0 degrees Celsius, right? So this is basically an increase in temperature. There's no change in state because you started with a liquid state here and with a liquid state here. So basically what we need to do is find these values. For Q, I'm going to call this Q1, and the energy for that change is Q2, right? So how do we get Q1? Well, Q1 would be equal to the mass of water, or mass of ice, water, whatever, times the heat of fusion. All right? So basically, we're going to take the mass, which is 10.0 grams, multiplied by the heat of fusion, which I wrote here, but I can't see it. What was the value again? I forgot. Okay, 335. All right, so let me go back to this here. Okay. All right, so times 335 joules per gram. All right. So that works out to be 3350 joules. That's for the melting part. And then for the other part, the equation that we're going to use is an equation that we met before. M times C times delta T, right? M is 10.0 grams times C, which is a specific heat, if you remember, which is 4.18 joules per gram degree Celsius, times delta T, which is a change in temperature. What's a change in temperature? It's the 20 minus the 0.00. So 20.0 degrees Celsius minus 0.00 degrees Celsius. And what does that give? Well, let's see. So that's 20 times 4.18 times 10. So according to my calculation, this works out to be equal to 836 joules. So therefore, the total heat required is equal to the sum of Q1 plus Q2, which is equal to 3350 joules plus 836 joules. So according to my calculation, this works out to be equal to 4190 joules. And that's how you do that. All right? Okay, so any questions about this? Any questions? Any questions? All right, one more thing I want to talk about, and then I'll get you started. Let me clear this here. Okay. Heat of vaporization. Kind of similar to heat of fusion. The only difference is that this is a heat that is required to basically convert 1 gram of a liquid into its vapor at its boiling point. All right. So basically, it's the boiling version, for lack of a better word, compared to what happens at the freezing point, right? So again, if I go back to the table here, the freezing point, or I should say, the heat of vaporization for water is 2259 joules or 540 calories per gram, all right? So going back here, we can work this problem here. So this question says, how many kilojoules of energy are needed to change 20 grams of water at 20 degrees Celsius to steam at 100 degrees Celsius? Okay, what is going on here? Okay, so basically, you're starting with H2O, liquid at 20 degrees Celsius, actually 20.0 degrees Celsius. We're converting that to H2O liquid at 100.0 degrees Celsius. And then at that temperature, you're going to convert the H2O liquid to H2O gas at the same temperature. All right? So basically, again, you need to find this Q value and this Q value. So I'm going to call this Q2, The first one is Q1. Q1 would be equal to M times C times delta T. M is equal to 20.0 grams times 4.18 joules per gram degree Celsius times the change in temperature, which is 100.0 degrees Celsius minus 20.0 degrees Celsius. And we need to work that out. So that's 100 minus 20 gives you 80. Multiply that by 4.18 times 20. And according to my calculation, this works out when rounded off to 3 sig figs, 6690 joules. And then now for the second heating process, we're going to multiply the mass times the heat of fusion, which is 20.0 grams times hold on, okay, if I remember correctly, the value is 2250 joules per gram. And that gives you 20 times 2250. So according to my calculation, that would be rounded off to 3 sig figs, 4.50 times 10 to the 4 joules. And I would add Q1 plus Q2 would be the sum of this plus this. So that's 6690 plus 4.5 times 10 to the 4. And according to my calculation, this works out to be equal to 5.17 times 10 to the 4 joules. And that's how you do that, all right? Okay, so those are just two examples involving heat of fusion and heat of vaporization. Okay, so with that said, let me just check something here in your assignment. Okay, so based on what we have covered, you should be able to do this assignment. For those of you out there in Zoom, let me make sure it's published so that you can have access to it. Come on. Okay, so okay, so let me just check to make sure it's there. Assignment 14. Okay, so for you guys out there in Zoom, I've just published it. So you can now have access to it. And for you guys here, and maybe I should help you guys out at least for the first couple of questions. So let me download this here. Ah. Okay, so the question, it gives you a graph. Let me make this smaller. So it gives you a graph. And the first question is, what is the vapor pressure of A? So the graph, by the way, is a plot of pressure versus temperature. This is the curve for A. This is the curve for substance B, right? So the question is asking, what is the vapor pressure of A at 35 degrees Celsius, right? So 35 looks like somewhere here in between 30 and 40. And it just so happens that it intersects with the line representing 26.7 kilopascals, right? So basically the vapor pressure of A at that temperature would be 26.7 kilopascals. And then for B, it's asking the same thing, right? At the same temperature. So in the case of B, the temperature is 35, right? So you may need to use a ruler to draw a line here, a vertical line here, and then draw a horizontal line here. And at best, this would be an estimation based on the scale here. It seems to be halfway between 0 and 13.3, which would be what? About 6.65 or 6.6, I would say. All right. And that's basically, the kind of thing that you'll be doing for the rest of that problem. In the case of C, it's asking what temperature, right? So it's the reverse or opposite of what you were asked in the case of A and B. What temperature is the vapor pressure of A at 106.6 kilopascals, right? So basically, 106.6 kilopascals is here, right? So basically, you have to drop a vertical line down. That looks like somewhere between 70 and 80. So by my estimation, I would say that's about 75, right? And so on and so forth. So if you understood those first three, then you should be able to do the rest of that question. Okay, I just noticed some questions being asked here in Zoom. Somebody was asking what chapters is covered by test number. I'm assuming you're referring to test number 3, Mr. or is it Miss? Who's it? Pelts. So the test is based on chapters 8 through 10, 8, 9, and 10. All right. And somebody else had a question here. Okay, Mr. Renfro. No, I have not yet seen what you have sent in Skype. I don't know when you sent it, but let me have a look now. Oh, okay. So apparently Mr. Renfro had a similar issue with the testing center. Okay, I'll have to, like I said to somebody earlier, I'm going to call them as soon as I get a chance. Later on this afternoon, to see what can be done, and then I'll make an announcement about that. And let me see here. Oh, this is somebody else. Okay.
Mr. Nicely, I have a question.
Yes, sir.
So, I had an issue with my fall tuition because it charged me for two of my three classes and it did not charge me for yours. So I went into financial aid today to see the issue, and it said that the reason it did not charge Bright Futures is because you put me as unattending in your class.
Okay, hold on. What's your name?
Hagen Peltz.
Oh, Pels. Okay, let me see here.
And
Pels,
they said
Pels,
that in order
Pels.
to fix that issue, you would need to change.
Okay, now I see the reason why. At least according to my records, you are not present for the first 2 days, for the first 2 weeks. So that's the reason why. Now, what I can do right now, in fact, I can change it since you have been attending since then. So let me do that right now. How
You're
do I
saying
do
that
it?
I didn't attend the first 2 weeks of
Well, I don't have
classes?
a record of it. You may have been here and I missed you, or when I call your name, you didn't answer or something. I don't know. But, whenever I hear somebody's name, I make a record of it. So according to my record, on the 15th and on the 20th, hold on. Yes, on the 15th and on the 22nd, I didn't have you down. I have you for subsequent weeks. But on the 15th and the 22nd, I don't have a record of you here. But I can, like I said, I can, I'm trying to remember, how do I do this again? I can make that change right now. I can remember how to do it.
Yes, please.
If I remember
They just said
correctly.
it's something you change in your computer, or that's all I believe. It's like you
Yeah, I
just need
can, I can, I can do it. I remember doing this once in my CF. I think, give me a minute. Let me just see if this works. Wi-Fi here is slow as I don't know what.
I believe I was here those 2 days, but I apologize if I didn't say here or make it clear that I was here.
Yeah. Yeah, I understand. I mean, sometimes stuff like that happens. Okay. No, not there. You go here. Okay, so, okay, I think I found the link. And this class is CHM 2025, section 40. And your name is Peltz. Okay, so I've changed it to has attended. You see, what happened is that we have a certain deadline date by which we need to indicate whether or not you have been attending class. And usually that is like after the second week or during the second week of class. So that's why, that's why I probably placed you as not attended, because according to my record, you weren't here. But
Okay.
hold on, let me save it. Can't forget to do that.
As long as you've changed it now, I should be able to email them and they'll get all that
Yeah,
sorted out. I just
yeah,
wanted to ask you.
I've just saved it, so everything should be fine now as far as that is concerned.
All right. I'll email them, and then if
Yeah,
it isn't fixed, I'll just.
if there's any issue, you can have them call me or email me.
Okay. All right. Thank you so much.
Yeah, no problem. Okay, so you guys are finished with the first part, question number 1. Finished? All right, now for question number 2, let me go back to, hold on, let me share my screen. And let me go to, okay, where was it? Okay. All right, so for question number 2, this bigger. It's asking how many joules must be added to 10.0 grams of water to raise its temperature from 10 degrees to 15 degrees. Now that's very simple based on what we covered in an earlier chapter, chapter 10. So what equation do you think you should use for this particular problem? Anybody? Let me give you a hint. Starts off with Q is equal to what?
M times C times delta T.
M times C times delta T. Thank you very much. So M is equal to 10.0 grams. C is the specific heat of water, which is 4.18 joules per gram degree Celsius. And delta T is a change in temperature. So we're going from 15 degrees Celsius minus 10 degrees Celsius. And that's basically it as far as the setup is concerned. So 15 minus 10 is 5 times 4.18 times 10. So according to my calculation, this works out to be, how many sig figs here? This works out to be 1 sig fig. So basically this will be 200 joules. All right. So that's basically how that is done. All right. Any questions about that? Any questions? All right, let me clear this here. And let me do this, and let me scroll down. And this question is asking, how many joules are needed to heat 20.0 grams of gold from 10 degrees Celsius to 50 degrees Celsius? And it gives you the specific heat of gold is 0.126. So again, it's the same equation that you're going to use. In this case, Q would be equal to the mass, which is 20.0 grams, times the specific heat, which is 0.126 joules per gram degrees Celsius, times the temperature change, which is 50 degrees Celsius minus 10 degrees Celsius. And what does that give? So 50 minus 10, that's 40, times 0.126, times 20. And again, this should be 1 sig fig, so that's 100 joules according to my calculation. All right. So those two are relatively easy. Now, for the next one, it says how many joules are released when 10 grams of steam at 100 degrees Celsius cools to produce water at 25 degrees Celsius. So let me clear this. Okay, so if you understood what we did in the last couple of examples in the PowerPoint, then you should be able to do this one. Now, one thing I want to mention, and I probably should have mentioned before, if you remember the heating curve that I showed you, basically as you heat your substance, water, for example, then basically there'll be a general increase in temperature. The opposite happens when it cools, right? When it's releasing heat, the temperature falls, and that's what they're talking about here. But the same underlying principles will apply when it comes to calculating the total amount of heat released, all right? So the question is asking for the amount of heat released. It gives you the mass. It gives you the fact that steam at 100 degrees Celsius, and it produces water at 25 degrees Celsius. So how would you approach this? Let's say you start with H2O gas at 100 degrees Celsius, right? And then it cools to H2O liquid, but the temperature is still 100 degrees Celsius, right? That's condensation right there. And then it cools further to H2O liquid, but this time the temperature is 25 degrees Celsius, right? So basically we need to find these two Q values, Q1 and Q2. So my question is, how would you find Q1? Let me do that here. Q1 will be equal to what? How do we calculate Q1? Remember, it's condensing. It's going from the liquid, it's going from the gaseous state to the liquid state. So how would you find the amount of heat released in that case? It would be equal to, it would be equal to the mass of the water times what? Not quite, because heat of fusion deals with melting. But it will be heat of something. It will be the heat of what? Heat of vaporization. And according to what I showed you earlier, let me see if I can bring it up here. The heat of vaporization is 2.26 times 10 to the 3 joules per gram. So the mass is the mass is 10 grams times 2.26 times 10 to the 3 joules per gram. All right. So this will be equal to 2.26 times 10 to the 4 joules per gram. All right. So that's Q1. And then Q2 would be equal to what? Now, Q2 is where we go from 100 degrees Celsius to 25 degrees Celsius, right? So what equation would you use for that?
M times C times delta T.
Exactly. So M is equal to 10.0 grams. C is equal to 4.18 joules per gram degrees Celsius. And delta T would be what? What's delta T?
75.
Right, 100 degrees Celsius minus 25 degrees Celsius, which gives you 75, right? So 75 times 4.18 times 10. So according to my calculation, this works out to be equal to, let's squeeze it down here, 3,140 joules. So basically the total Q1 plus Q2 would be equal to 2.26 times 10 to the 4 joules plus 3,140 joules. Let's see what that gives. 2.26 times 10 to the 4 plus 314. So according to my calculation, that would be equal to 22900 joules. And that would be the answer. All right. Okay, so that's basically it for this assignment. All right. So your upcoming final exam will basically cover everything up to and including what we just completed today. All right. As far as this assignment is concerned, you can turn it in now if you want to, or you can submit it online if you want to make sure it's neat and tidy and everything. It's all up to you. For you guys, you need to turn it in online, of course. And before I forget, let me clear this. And then let me do this. I'm going to set up a Dropbox for this assignment. Oh, already did. Okay, let me just check to make sure it's actually set up properly. Okay, so you should be able to turn it in. I've set a deadline date of tomorrow. So you can turn it in then, all right? Okay, so that's it. If you have any questions concerning the final or anything else, feel free to contact me during my office hours. Have a nice day.
Quick question.
Yes, ma'am.
As for the test, you said that you would be contacting Wanda Lee, right? I don't have to contact her.
Yeah, well, no, I don't think you have to contact her. I'll contact her, and then whatever the result of that conversation is going to be, I will post an announcement in Canvas about that.
Okay, thank you.
I have another question.
Yes,
so
sir.
if I have my appointment to take the test later on today, if I have the same issue, I just watch for your announcement.
Yeah. But hold
Okay.
on, but if you have an announcement already, I mean, if you have an appointment already, that means you should be straight.
Well, they let you make the appointment, but then you wouldn't know until you go in.
Oh, really? I didn't know that. Okay, I
In
thought.
my mind.
Okay, I thought that once you got the appointment, that's it. I mean, all right.
Yeah, because that's
yes.
the same issue I had. I made an appointment for this morning, and when I went, they didn't let me take the test, so I just made one again for today at like 5:30 or 6.
Oh, okay. All right. Yes. Okay. I definitely have to call Miss Lee, and like I said, whatever the result of that conversation is, I'll make sure to inform you guys about that. All right.
All right. Thank you so much. Have a good day.
Yeah, you too. Take care.